So this lecture I think will be easier. We will discuss some operations on vector fields. So actually, a vector field is a special vector attached to the points, and then probably the physical meaning or geometrical meaning will be clear later, just in a moment. So all I want to say is usually you can visualize it in 3D. So the following is following formal definition. Let D be a set in R2 or R3, even Rn, no big difference. A vector field on R2 is a function. So vector valued function f that assigns to each point x, y in D. So if in 3 dimension, then x, y, z in D are two-dimensional vector f, x, y. So in 3D, there will be a three-dimensional vector f, x, y, z. Okay, probably it's better to draw a picture. So suppose this is the domain we are interested in. So vector field f just assign some vector for each point in this domain. Okay, and by the definition, you see the assignment could be arbitrary. We don't need to assume it's continuous function, smooth, or whatever. But usually when we study it, we will assume it's smooth, because then we can take derivatives. In fact, in reality, most of the time we will have at least piecewise smooth vector field. Okay, and then numerically or quantitatively, we can represent fxy in the following forms, component-wise. You can either write down in this way, so where p, q are functions, just real valued functions, or sometimes you might want to write down as p, q, parentheses. Or sometimes if you don't want to emphasize the variables, then you just write down like this for short. And the point is where here p, q are scalar functions. So if f is in 3D, then we can write down as p, q, r, three components. Oh, sorry. I, q, j, r. I, j, k. Yep. And some similar format I will just omit for 3D. Okay, then geometrically, there are some very interesting examples. First, suppose xy is given by the following formula: negative yi plus xj. So, for example, when x when the point is on the positive axis, then you might find the vector field should point towards the positive y direction. And when it's in positive y direction, then the vector points to the negative x direction. And similarly, you can draw this, and if you shrink a little bit, you might find the magnitude is also shrinking. Sorry. Okay, then what do you have? You might have this kind of thing, and you have some point here, very special. Because it's zero vector here, seems like you have a bunch of circles shrinking down to the origin. Okay, so this is the first example. And at the end, we will show what's the significance for this type of vectors. Second example is given by, suppose you have the following vector x, y, z equals z, k, then what do you have? So for each point, if it's above the xy plane, then points towards to the positive z direction, otherwise points to the negative z direction. And on the xy plane, so the vector just zero. Just zero. On the xy plane, there's nothing. Okay, and you will find there's no circle phenomena here. So this and this are different. Circle phenomena means you have a curve, closed curve in the region such that the tangent vector of this curve just a vector field here. You can do this for example 1, but you cannot do example for example 2, because whenever you trace a point in example 2, so if you're along the vector field, you always go to infinity, either go to positive infinity or go to negative infinity. You cannot form a closed curve. Okay, and so those better showed by the picture. Next, we will give some example which are better showed by the numerical formula. So this is called gravitational field. So for simplicity, let's choose the following notation: x arrow over arrow. So x1, x2, x3. And this notation is better for higher dimensions, because if you have n dimension, x, y, z, w, and what is next, but if you use x1, x2, xn, you can formulate as many variables as you want. So f is negative at small m, capital M, g, and over norm of x to the cube times the vector x. And here, small m, capital M, just the mass of two bodies, and g is gravitational constant, so you can view them as constant mathematically. And then if you compute what is the magnitude for these vector fields, so for each point you might have this is positive m, capital G, r squared, where r is x squared plus x2 squared plus x squared 3 squared. So this is just a Newton law, just what's gravitational between point mass with distance r, inverse square law. And if you draw the picture, so those fields, so notice that here you have negative sign here. So if you draw the picture, all the fields just point towards the origin and contradicts with this one, the first one or second one, the magnitude is increasing. Is increasing because you have singularity here when r goes to 0. Okay, and this is not the only example in the nature had this kind of mathematical formula. We also have the Columbus law, electric force, which gives you the following. So those are constants as well. They have a distinct physical meaning in physics. And then here, x, just your position vector. And the electric field. Electric field is electrical force per electron. So you have this, and no matter how mathematically they have the same feature, they just have vector of its length cubic. So they also obey the square inverse square law. Okay, it's not an accident because you can check the only power satisfies the Laplacian equation is the cube in dimension 3. So this is very important. Of course, you cannot take x to be the origin because it's not well defined here. It's also true. You don't need to know this, but all I want to say is this exponential is important if you want to understand the quantitative property of this field. If you only want to know the qualitative, then this index bigger than 2 is enough. Okay, we will come back to this topic later, but then we will introduce another way to construct vector fields. So suppose f is a scalar function. Then before we define what is gradient f, this is x derivative I plus y derivative j. Here we assume f is in xy plane. It's defined on xy plane. And if you're in 3D, then you have fx I, fy j, fk k. And the example, you can assign any smooth function to be your f, and then the corresponding gradient f can be computed in this way. Okay, and x derivative 2xy I minus, plus x squared minus 3y squared j. And now we ask the inverse problem. So, which vector field is a gradient field? So before that, actually we can first give a necessary condition. Necessary means if the vector field is a gradient field, then the following condition must be true. So we define the so-called conservative vector field. We call a vector field F a conservative vector field if there exists a function f such that the capital F equals the gradient f, and then the corresponding small f is called the potential function. Okay, now let's use a gravitational field. Oh, I see. Sorry. Here, my bad. This is not the necessary condition, just another name. Another name for the vector field. The necessary condition will be given just in a moment. So they're saying, you can see this is a conservative vector field, or you can see it's a gradient field. They're same. This name comes more from the physics because you have a potential function. Whenever you have potential function, the potential just conserved by the field, by something. Okay, let's see. Gravitational field has potential. So F. So recall what is gravitational field. If you are not satisfied with the constant, just forget about that. As I said before, the only key feature is x over norm cube. And the following is a little bit non-trivial thing. You need to really do computation. So question, I'll leave it to you. Gradient f is capital F. Okay, now we want to introduce so actually here I didn't see explicitly, but I would emphasize to you now. We gradient f gradient is an operation on vector fields. And if we specify, oh sorry, gradient is on, sorry my bad, it's on functions, but the range is vector fields to vector fields. Okay. Next, we want to introduce. So question, probably first, can we find some good or common or useful operations on vector fields? So the answer is yes, and usually they come from geometry, and I would like to see this will be strongly related to the topic in this chapter. Oh, I should say, this is a new chapter. Chapter 16 probably. Okay, now, so first one we would like to introduce is a curl or a vector field. And how to define it. Let's first do 3D this time. Partial R, partial Y. The formula is a little bit difficult to memorize, but just in a moment I will give you another way to formulate it. They're equivalent, and but the second one probably is easy to remember. Okay, and so if we introduce the following one, so this is a definition for curve. And next, we introduce the gradient with an arrow. So if you do latex, this is called a nebula. And this we define to be I partial x plus j partial y plus k partial z. Okay, you view it as a vector, and but just formally, each position you have some operations. You have some differential here, and then what is curl? Curl can be written as nebula cross f, curl f should be. And if we still remember how to compute the cross product ijk, and then you plug in the coefficients for the first vector. Although it's differentials, we view it as vector, and f you have three components, P, Q, R. Okay, now let's expand this. So first you have partial Y, R, partial Z, Q. So here you have partial R, partial Y, minus partial Q, partial Z. Exactly this one. Okay, and then you have plus J, sorry, minus J. Remember you have minus sign here. And then you have this way and this way. So partial R, partial X, minus partial P, partial Z. Okay, so if you do distribution, negative is positive, and negative is negative. So you have the second term. And lastly, you will have K, so which is partial Q, partial X, minus partial Y, partial P. So my suggestion is, if you can remember this formula, that's good. If you cannot remember it or suddenly forget it because of nervous or whatever reason, you just do the cross product. You will get the formula directly. But so let me first write down this formula. This is a usual formula you will see in your engineering textbook or physics textbook. But you really should know the meaning of this formula. Although it's concise, but you need to do some definition a priori. And so here I would like to do some remark. As you know before, this is different from this one because of the property of cross product. Even you can define the right hand side, although here we don't have definition for the right hand side. This is just a formula. It's a way for us to remember the formula. Okay, so now let's do some example. Suppose you have vector field F xzi plus xyzj minus y squared k. So you need to find the curl F. Solution. Curl F equals ijk partial x, partial y, partial z, xz, xyz minus y squared. This is I times, so negative 2y minus xy plus j, sorry, minus j, and 0 minus x and plus k, yz minus 0. So therefore you have negative 2y plus xy I plus xj plus yzk. Okay, next we want to introduce very important property, and which will give you a necessary condition for a vector field to be a conservative vector field. So theorem, but the proof is very easy. Curl gradient F is sorry. Yeah, use in your textbook, they will not distinguish this gradient and the above over arrow nebula. So, but in this course, I will do some distinction between them. This is pretty easy if you remember the formula. So it's ijk partial x partial y partial z and partial fx, fy, fz. And then you have I times partial y partial z minus partial z partial f partial y plus j minus j partial x partial f partial z minus partial z partial f partial x plus k partial x partial f partial y minus partial y partial f partial x. And it's easy to see you have cancellation because of the commutative differentials. Okay, so this is this theorem. So the corollary, as I said before, corollary just a usual notation for some properties follows from the main computation, main theorems. Or in other words, very easy to compute. Or very easy to derive. So corollary is if f is conservative, then the curl of that vector field is zero vector field. So let's do one more example, show that f equals xz xyz minus y squared is not conservative. Solution. Because we can compute curl f. We compute just above, so we can copy the answer here. 2y plus xy I plus xj plus yzk it's not a zero vector. Okay, before we move on, I should make a very important remark. So here curl, let's consider it abstractly as an operation on vector field. Where does it go? It goes to vector fields as well. Okay, this is very important. Because you see, what we have here is vector fields functions goes to vector fields. Here you have vector fields goes to vectors. Although sometimes in 2D we will have a little bit different notation. I will tell you later why we use the notation as a scalar, but in general you should keep in mind you always have vector field to fields for curl operations. Okay, and then we can discuss a little bit about the intuition behind the curl. So suppose you have water flows in 3D. So water flows, and just like you have you are doing laundry, and then you have something spin inside, and then what is curl? So suppose this point x, y, z, curl f, x, y, z. So curl, the physical meaning is flow, rotate around this point, around this vector. So just give you some axis where the flow rotate around. Okay, and then it immediately follows if curl F is a zero factor. What does that mean? That means you have no axis for the flow to rotate. So the fluid is irrotational at XYZ. Okay, so this is for curl. Later on, we will, just in a moment, we will define what is divergence. So I would like to first tell you what is divergence. This physical intuition can be given without the intuition. Sorry, without a formula. So I will give you two types of flows. We're still considering the flows. And then you can easily see what's the difference between, oh, actually I can draw one more. So there's no source, no sink, and there's a source inside the box, and there's a sink inside the box. Okay, then what is divergence? Let's call those vector fields as F. F so represents the net rate of change, the change of the mass flowing through the small cube at XYZ. So here the most important thing is net. Let me use red one. Oh, sorry, blue one. Net. You see from the first picture, although you have flow in, but then you also have flow out. So you can imagine all the water flows in, then just goes out. And for the second one, you have some water just flows out from nowhere. There must be some source you cannot see. And then the third one, everything just squeeze in the small box and they disappear or they stuck there. You have sink there. So let me call first one, second one, third one. And then by the definition, geometric definition, you will see so divergence of F so is 0 in case 1 bigger than 0, less than 0, because flows out, less than 0 in 2, bigger than 0 in 3. Just by this definition, we can qualitatively draw this conclusion. Okay, next we will do some formal definition of the divergence. So what is divergence? Suppose you have vector field F equals P, Q, R. Then divergence of F is the function defined by divergence F equals partial x plus partial q partial y plus partial r partial z And here the one of the keywords is function. And if you can remember this correctly, you can use the following notation. The gradient vector dot product with your vector f. Okay, now let's compute a little bit. So suppose the vector field you have is xzi xyzj minus y squared k. So what is divergence f? So you just plug into the formula, partial p partial x partial q partial y plus partial r partial z. So it's z, take x derivative for this guy, y derivative, so you have x and then plus y derivative of this guy, you have xz, and then plus the last one is this guy, you have z derivative of y squared, negative y squared, which is 0. Okay, then you are done. And now we have the following important theorem. So first condition, just a notation. Suppose your vector field is in 3D, and then divergence curl f is always 0. So prove I should say, yeah, I will first prove this theorem and then just make up the an important remark. So the computation is, remember what do we have for the divergence? This is partial x and partial y, partial z, and the inside you have partial r, partial y minus partial q, partial z, partial p, partial z, minus partial q, partial x, partial q, partial x, minus partial p, partial y. If you can remember this clearly, which I cannot, and then you can compute this. So the most important thing is you have cancellation. I will use different colors to indicate the cancellation. So here you have xy derivative of r. Then you should look for so here you should have r. So partial AP. Sorry. We made a mistake. Okay, partial r, partial q, and then pqry. Partial z, partial x. So here you have r, you should have. Okay, then you have cancellation. This one with this one, blue one, q. For this one with this one, and for r, you have this one for this one. So finally you have 0. Okay, if you are not satisfied with this method, then let's do some fancy stuff. Okay, so this will be delta dot ijk. So partial x, partial y, partial z. Oh, probably you can write down the components also here. Dot partial p, partial x, partial q, partial y, partial r, partial z. Okay, then you do this dot product, you just replace ijk by the three components corresponding here. So partial x, partial y, partial z, partial x, partial y, partial z, partial p, partial x, partial q, partial y, partial r, partial z. Okay, now what do you have? So the tricky thing is, if you know a little bit linear algebra, you can do expansion. Or even if you don't know linear algebra, it's fine. You just do the formula. You fix this one. Okay, so let me write down a little bit. So partial x, you fix this one and compute the subdeterminant here. Partial y determinant, partial z, q, partial y. Okay, so this is not correct way. Yeah, eventually you need to expand the last row. Expand the last row. I leave it to you if you are interested in this. Leave it to you to figure out. If you expand the last row, then what do you have? Then you will have this situation here. So the operators just the same, just zero, just cancels out. And for the middle one, you have this, and then you have this together, and then for the last one, you have this. Okay, so the remark I want to make long time ago is the divergence. If you think about, this is from curl. Sorry, this is from vector fields to functions. Okay, always keep in your mind this. So now let's apply the above theorem a little bit. So recall, what is a theorem? Theorem says curl or a function must be divergence free. So example, suppose you have function like this. So show that f cannot be the curl of a vector field G. So first, by the previous computation we had, we can compute again. So divergence V. What is divergence V? So we already computed. So here. So this is not zero. Okay, and if f is curl of certain G, then divergence f should be divergence of curl G, which is zero by previous theorem. So it is a contradiction. So therefore, this assumption is not true. The theorem is true. Okay, so the universal view of all three operations on vector fields or functions can be put together. So you start with a function. Start with functions, and then you have vector fields. So remember, the operation here is gradient, and then you have vector fields to vector fields. This is curl. and then you have vector fields to functions. You have divergence. Okay, and the formula we learned before is that suppose you have function. So first property we have. Suppose you have function gradient curl is 0. What does that mean? So that means if you have f here, you do one step goes down, second step goes down. You always have 0 after 2 steps. Okay, then for second property, mathematically you can write down as divergence curl of vector field f is 0. Then what does that mean? That means if you start from this position, go 1 steps, you might have some arbitrary vector fields. But then if you do the next step, then you will have very good property that it's always 0, or I should say always 0. So here is the same property, always 0. Yeah, so that's a very convenient way to remember this. If you later on learn some differential geometry and advanced mathematical class, this is called exact sequence, which characterize these properties a lot. Okay, so I think I will stop here for this lecture. Next time we will talk about the line integral.